Well, our next speaker is Aaron Cole, uh, who works now in
University of
Utah.
Thanks, Alvaro. It looks like the microphone is on. Hi, I'm Aaron Knoll from the University of Utah. I'm also do a lot of work with Argonne National Laboratory for the past several years. I've been a guest researcher there. And this is sort of a summary of work that I do with the Intel OSPRay team. And that will hopefully benefit a lot of the work that's going to happen at Argonne National Laboratory for its users and visualization staff. So just a quick, brief background. I work at the University of Utah at the Scientific Computing and Imaging Institute, which has a long history of work in the field of visualization. And really, among other institutes like EVL was key in this idea of viz as graphics for science and more. The Utah Intel Parallel Computing Center and this new Intel Visualization Center have several faculty and staff involved. Myself, Ingo Wald, who's sort of the Intel side, Chris Johnson, the director, and several other professors. And our goal there is to really modernize visualization the way it's done currently, and specifically to leverage Intel hardware to do this. In the past, we've done this almost exclusively on GPUs when we're talking about hardware for graphics or viz. And we think that there are reasons to use CPUs and Xeon Phis as well. And certainly a big part of that is collaborating with national lab partners. So definitely our partners at ALCF, but also inside users and scientists at Argonne. For example, MSD, CSE, and CNM have given us a lot of our data sets and use cases over the years. So my talk will be about why we'd want to do visualization on CPU and Xeon Phi. And this is really largely, I should say this is really a talk on behalf of Intel, of Jim Jeffers and Ingo Wald. So I'll go over their software-defined visualization and high-fidelity visualization frameworks and their vision for why we should do it. And then I'll talk about OSPRay, which is a collaborative effort. It's largely driven by Intel, formerly Intel Labs, and now Intel TCG. But it's also really, it's an open source framework, it's an open API, and it's starting to get a lot of collaborators from outside Intel, and certainly a lot of research projects that I myself have been involved in and we hope to share with others. Then I'll talk about production use cases for OSPRay and research that I've done with OSPRay. So why visualization? I mean, probably don't need to explain too much of this to this audience, but visualization has really evolved into maybe the fourth pillar of the scientific method. So if computing, scientific computing would be the third pillar, visualization is really what you need to be able to see the results of your computations. And there are simple sort of crass reasons for doing this, like communicating it to audiences who might not understand it, but it's also useful in analyzing your simulation code and validation and debugging. And we need algorithms that really let us do this, not just on a specific piece of hardware, but really on any platform, and especially, ideally, the full supercomputing platform. We need to scale to both compute and memory resources to be able to tackle the largest data possible. And we really need to do research that advances state-of-the-art in the future, but also to some extent supports production needs of viz software today. So it's a fairly diverse problem. And to give you an idea of why we care about more than just GPU support for visualization codes, we'd take a look at what supercomputers are today and what hardware they are largely composed of. And if you look at all but 2 of the top 10 and the top 500, these are largely CPU or Xeon Phi based supercomputers. So if you want to run visualization on these machines, you really have to be thinking about how do you do viz on CPU and on Xeon Phi. And I think there's also this question of, is viz natively a big compute, fast compute, lots of flops, GPU-ish problem? And one way of looking at this, at least my opinion, is that for some of the largest data, in fact, it's not. We care much more about how quickly can we access large amounts of memory randomly spread all over memory and disk. We care about that much more than how quickly we can process this from a compute standpoint. Some of the new Uinta simulations that we've been running, and I think are part of the large inside allocation here at Argonne, very often these will generate 1 to 2 terabytes per time step. And if you saved everything out to disk, you'd have potentially petabyte or exabyte runs. So post-processing this data is just not really practical in a lot of cases. And this has resulted in a lot of interest in situ analysis running on the supercomputer itself, and generally much less I/O. And also, visualization is costly. If you do use a GPU cluster for all of your viz needs, then very often, just because of memory limitations, you have to use most of that GPU viz cluster just to be able to digest large data. And that's fantastic in a lot of use cases where you need to do that, but you also don't want to be in the position of having to burn 100 million hours just on viz codes either. Having the CPU as an option is good. And yeah, lastly, Xeon and Xeon Phi. Xeon Phi with its up to 384 gigabytes of memory really do enable larger working sets, data sets like the hack cosmology runs, which are some of the largest scientific computations that we know of and that we have today. So in short, this means we really do need viz algorithms that run on any platform, ideally GPUs and CPUs, but not just one or the other, and do scale. So this leads us to a term that I think Jim Jeffers at Intel coined called software-defined visualization. And the idea here is to treat viz as a general compute problem and not a specific algorithm plus graphics hardware, or I should really say graphics API problem. And again, this means doing viz on any compute node, not just visualization nodes. Support viz during and perhaps inside compute runs, so either tightly coupled in situ or in the compute code itself. And again, this allows us to scale to full host memory, which is 1 or 2 orders of magnitude greater than GPU memory very often. Then another advantage is the ability to use this exact same software and no change in code on a laptop, workstation, or HPC resource. Maybe you'd recompile, but the underlying code would be more or less the same. And lastly, to leverage algorithms such as ray tracing that scale better on CPU and many core architectures. So that just are inherently scalable. And the overall idea here is that compared to rasterization-based graphics of the past, ray-traced large-scale visualization, it's really a different problem. It's really a different use case from what you see in computer games, and much more akin to big data and big HPC needs. So how did Intel do this? So there were basically 2 prongs to their software-defined visualization initiative. One was to build on top of existing APIs, such as OpenGL, which is great because you can immediately just drop this in with your polygonal graphics pipeline. For example, VTK, Parent View, and Visit, and it will just work. And the challenge with this is that it doesn't really work super well on the specific hardware, and it will never, without a serious consumer push, it just won't ever compete with graphics hardware in performance or features. And the other option is to create a new visualization technology or new API that's not limited by the existing i.e. OpenGL API. And the advantage of that is that the sky's the limit. You can use new programming models, you can use new algorithms, not just ray tracing in general, but really algorithms that are fine-tuned to scientific data sets. And you can adapt to use cases in HPC and Viz specifically. And the downside to that is that there's some adoption cost and it's not going to be the same as OpenGL. So this is roughly what Intel created. The top is this OpenSWR or OpenSWR, depending on how you pronounce it. Yeah, I know, it's a great name. And the bottom one is the OSPRay Ray Tracing API for visualization. So OpenSWR, yeah, forgive me. OpenSWR is actually quite good at what it was designed to do. And what it was designed to do is rasterize things fast on SSE, AVX, AVX512, specific KNC intrinsics, and now KNL. So for rasterization of data sets on Intel platforms, it's really fantastic at that. I'm not going to spend too much time on this because Sylvia will go over some slides, and the big challenge that OpenSWR has is that it is not a full competitor or replacement for hardware accelerated OpenGL. It was, in a sense, not really designed to be. It rasterizes really fast and effectively, but if you have heavy-duty fragment shader code, then it basically uses Mesa LVM pipe, and you're going to be bottlenecked by that. And there's very little that Intel has done specifically to support that. That might change in the future if there's enough community need or community interest, but I think that's the limitation of OpenSWR right now. So it's great for lots of triangles. I'd argue there are still better options for lots of triangles, but it's not going to be necessarily the best solution for fragment shader heavy code. But anyway, these give you an idea of how it performs in comparison to GPUs. I'd say overall on Xeon or now KNL resources, if you're rasterizing things, it's going to be very fast, and in some cases faster than GPU equivalents if you have really large data. But again, if you have shader code, then it's maybe not the best solution. So going on to high fidelity visualization. The point of high fidelity visualization compared to software-defined visualization is not to just find ways to do things in a more scalable fashion on Intel hardware, but create visualizations that are actually better than what you could get from rasterization. And the chief idea here is to use ray tracing instead of rasterization as the base algorithm, even if you're only shooting primary rays, even if you don't have more advanced effects. So the advantages obviously are that you can have more advanced illumination effects. You can have shadows, ambient occlusion, global illumination. But you also have support for things that don't just naturally come to rasterization pipelines, like progressive and adaptive rendering, support for non-polygonal geometry like glyphs, streamlines, analytical surfaces, which you can do in the GPU rasterization pipeline, but certainly in a slightly more roundabout fashion. So this, when this effort started up, Intel did not have a specific visualization product. They had something called the Intel Embree ray tracing kernels, which are essentially a collection of hand-tuned fast acceleration structures optimized for Intel architectures at the time, AVX, AVX2, which was a fantastic place to start, but you couldn't really turn this over to the Viz community and have people adopt it the same way they would OpenGL and GLSL. There was no support for volumes or glyph data, nothing like 3D textures. And this product, Embree, still exists. You can go get it, and if you want to build off of a low-level ray tracing acceleration structure code, it's fantastic. But it was obvious that to support visualization, we needed something bigger than that, which leads us to OSPRay, the CPU ray tracing framework for scientific visualization. So to give you an idea of what OSPRay is trying to do, this is a standard rendering of this magnetic resonance volume in ParaView and OpenGL. It's generating a few contours, a few isosurfaces. Each one has a different color. On the whole, there's probably on the order of maybe 20 gigs of triangle data here. So it's basically a big triangle soup. It would be too big for the GPU and it's in fact pretty slow to rasterize just because you have a lot of triangles. Obviously, if you had less triangles, it would be really fast. And just naively, with no real changes to the software architecture, you're able to get shadows, ambient occlusion. You're able to interactively render this on pretty much any CPU resource that you have. Obviously, the more CPUs, the more cores, the better, and KNL definitely counts as a high core resource, but this is sort of the look that you're able to achieve compared to standard OpenGL. And similarly for volume rendering, this is a newly added feature that Carson Brownlee on the Intel OSPRay team has been working on furiously over the last several weeks. Originally, with standard volume rendering, you'll be able to achieve effects like this. Again, this is with no lighting, so you can probably do better. And with ambient occlusion and shadows, in OSPRay, you're able to achieve effects more like this. And the idea is that this would be just built into the software and anybody could use it. And anyone who ends up calling the OSPRay ray tracing library. And here's one last example. This is without any lighting or shading, and This is with ambient occlusion and shadows. Again, this is volume rendering, not isosurfaces. There's no fixed geometry here. So that's, in a nutshell, what OSPRay is aiming for, is the ability to just trivially support ray traced effects without even having to think about it or having to create a special implementation. The things that build on top of Embree are things like frame buffers, cameras, scene and data management. Obviously, compared to Embree, it supports non-polygonal geometry, which is great for streamlines and glyphs. It supports volumes as a first-class citizen, currently just structured volumes, but we're working on structured and AMR-type volume data sets. There are some challenges there, and I think we do need to work with the community to a greater extent than we have, because there is not really a one-size-fits-all structure for a lot of these data sets. Underneath the hood, OSPRay uses the Intel SPIMD program compiler, or ISPC, for fast vectorization. It really is a lot like GLSL. If you're used to GLSL or CUDA, then you are writing SPIMD code with some modifications, some semantics like the uniform keyword, but more or less this feels like you're writing shaders to do graphics. So for people from a graphics background, it's not going to be completely foreign. And it uses thread building blocks. TBB is currently the fastest execution model that we have for threads. We do have an OpenNMP execution model and also a Silk Plus one. And depending on what you've compiled with and what time of year it is, one of those will be faster than the other. But really what OSPRay is giving you is a easy-to-use rendering API for visualization, not just for rasterized graphics plus, but really for visualization workloads. And we've already integrated this into some production packages, such as ParaView, Visit VMD. So just to give you a quick and dirty idea of what this viz code would look like, and I apologize for the poor quality of the graphics. With all the images, these slides ended up being about 100 megabytes, so I had to compress. But this is just a basic idea of what an OSPRay invocation code would look like. It's very similar to what you do in OpenGL, in some ways even a little bit cleaner. It doesn't force C++, you can call it from straight C, and with some bindings and a lot of effort, Fortran. But that's the basic idea. So I mentioned it supports non-polygonal geometry such as glyphs and implicit surfaces. So for molecular viz, for the large particle visualization that we've done with some ALCF users here, this is a great idea, I think. But also implicit isosurfaces, you're able to render surfaces from this data, the Rickmeyer-Meshkov data set or large volume data sets with very little memory footprint. And if you have polygonal data, for example, if you're using ParaView or Visit or a production tool set like that, and you're willing to deal with very, comparatively high memory overhead, you can still achieve a lot of these effects, and they look great. I mean, you're using Embree under the hood. All of these examples were interactive in OSPRay, and in many cases, they're using ray tracing, and in fact, they could use full path tracing. Of course, they wouldn't be as fast, but that's the basic idea. And again, with the integration code, the idea is that you just enable a checkbox, and all of a sudden you're using OSPRay, and you can enable another checkbox and activate ambient occlusion or global illumination. For structured volume rendering, I'd say this is a lot less fancy than a lot of the GPU options. And if you're comparing, as we will very shortly, apples to apples, GPU versus CPU versus KNL performance for small volume data, the GPU is going to be really fast, much, much faster. But once you get sort of past the 1 to maybe 8 gigabyte mark for a lot of these volume data sets, somewhere around there, a funny thing happens. On the GPU, you hit the PCI bus. So in a lot of cases, you won't be able to render the large data, and if it does, it's going to take a really long time. Whereas on the CPU, you keep on chugging along, and you're getting 15, 20 frames per second, 40 frames per second for hundreds of gigabytes worth of data. And it's just in memory and core, and it works just fine. So overall, in terms of OSPRay performance, and again, these are not KNL numbers. These come from the OSPRay IEEE Viz paper that we submitted a few months ago. But we're finding that just for compared to rasterization, primary rays end up being, in a lot of cases, about 8 times faster than large triangle data. For example, this 300 million triangle Rickmeyer-Meshkov isosurface. And another just example is large volume data, where the Rickmeyer-Meshkov data set was about twice as fast as the OpenGL volume renderer in ParaView. And again, these numbers, you have to take them with a grain of salt. I mean, it's always possible to create a better GPU implementation or even a more intelligent CPU implementation. But the idea is, in OSPRay is that it's an API, it's a reasonably well-implemented system, and you use it and it just works. So yeah, that's where you can get it, osprey.org. And there's a link to the IEEE VisWeek paper if you're interested in more details. Current improvements to OSPRay and SWR. OpenSWR is available through the Mesa library. Actually, Silvio Rizzi has recently gotten it, so I'll be able to tell you more details on how to get the latest OpenSWR version and how to run that. It's mostly just you run it straight out of the box, and you might have to change the library path, but it will work exactly immediately with all the code you already have. And recently, OSPRay version 1 has been released. So it's out of alpha, possibly still in beta, but it's version 1 on GitHub. And things that the OSPRay team is working on is a sort of a cleaner data parallel API to get this adopted in a cleaner fashion in software like ParaView and Visit, and some frame buffer and tile display work, and support for volumetric effects for global illumination in volume rendering. So I can't do it from this machine, but if anyone wants to see some live demos of ParaView running on a large memory machine, I'd be happy to fire those off. In the current ParaView binary, you just download it from the ParaView site, and you check the Enable OSPRay box, and you're basically rendering with OSPRay. And in fact, if your data is at all large, I would absolutely recommend this. I would check the render with OSPRay box before you load or try to render large polygonal data, because with a lot of the GPUs, it might actually crash or hang or take a really long time if your data is large enough. Whereas with OSPRay, you really do not have this worry. And John Stone recently integrated this into VMD 1.9.3. So if you do a lot of molecular visualization and you have large geometry coming from that, then you can use OSPRay in a very similar way. And as a quick disclaimer, I should say I have not used this yet, but this is what John passed along to me just recently. So this is available from the VMD, through the VMD download website, and it should be available as of 1.9.3. So research in OSPRay. This is what myself and the Utah IPCC have been predominantly working on in collaboration with folks at Argonne National Lab, like Mike Papka, Joe Inslee, Silvio Rizzi, Venkat Vishwanath. I think the reason you'd want to do this is that SciViz research has been largely GPU focused for a good portion of the last few decades, and there are obviously good reasons for that. I mean, when you look at algorithms like volume rendering, for the longest time, those were really expensive, and there's this question of could you actually just get them to work at all on any size data fast enough? But when you talk about OSPRay and CPU-based visualization and PHY-based visualization, you all of a sudden have these questions of what do you do if memory is no longer a limitation, if you don't have to think about in-core versus out-of-core? Can you do in situ directly from the compute code using this? Which scientific applications can this help specifically? And I think the bigger open question is, can DOE start to leverage this in its own research? So one of the first, I guess, OSPRay-driven research pieces of work that I worked on with Ingo Wald and some of the Argonne folks and at least one scientist at MSD was this idea of the PKT structure. And the idea here is that if you just use OSPRay with no changes whatsoever, you would end up having a very high memory overhead, which is ironically exactly what you're trying to eliminate by using CPUs and by using an infrastructure like OSPRay. But if you just use the stock Embree bounding volume hierarchy, you'll end up with a 4x overhead cost. And instead, what you can do is you can write your own ISPC kernel. You can use this balanced KD tree acceleration structure, which is really just a reordering of the original particle data. And it's a little bit slower, but basically very fast to build. And you can render data like this with effectively no memory overhead, or very, very little memory overhead. And you can do this with ambient occlusion, global illumination, everything that a ray tracer supports. And there are issues. I mean, certainly anytime you deal with 100 million or several billion particles, you're going to have aliasing unless you correct that. But more or less, this is something that you can run on a CPU workstation, and certainly now a KNL, and you're going to get interactive frame rates and be able to ray trace basically as large particle data as you want. So this came out of our Viz 2015 paper. Here's another example, a 30 billion particle data set on, that occupies about 450 gigabytes on disk. And this was actually kind of interesting because, first of all, you could tackle a data set this big on a single CPU workstation, in this case, a 72-core Xeon workstation. And a KNL would probably perform about a third as fast as this workstation currently, but it would be able to tackle similar orders of magnitude, similar sizes of data. And I think that this work was actually very interesting because right about at the same time, Silvio Rizzi was doing, or looking at similar data on the GPU in Argonne's VL3 software. And he was able to use a splatting and LOD algorithm to quickly and efficiently render similar size 30 billion particle data sets, admittedly coming from a different cosmology code, but in a sense a similar data workload. And these are completely different algorithms. The data sets look similar, but on the top you basically have ray traced or path traced opaque spheres. On the bottom you have transparent splatted glyphs. So in a sense it's sort of an apples and oranges comparison, but you still end up having an algorithm that you can actually run on a single workstation and be able to see the entire data set. And this, in a sense, was in a way competitive with a 128-node GPU cluster. And I'm not saying you should always use the cluster or always use the workstation, but all of a sudden you have a different option for tackling large data like this. And moving forward, we've started to explore how could you use this algorithm for loosely coupled in situ. Tightly coupled would be interesting also, but that's in a sense where a lot of this research could go. Is you could use this for both compute and rendering and just call OSPRay from any compute code anywhere at any time. And this paper that we recently, my student Will presented at ISC, was interesting because it was actually a lot more complicated than we thought it would be. So there's more work that really needs to be done in this area, I think. And I think moving forward, you have very interesting questions when you start to bring this to research codes outside of core OSPRay. You know, in the Visus infrastructure at Utah, you have this question of what does out of core mean? In something like VL3 at Argonne, where you have large-scale distributed parallel rendering, you have this question of can you actually use these sort of direct methodologies where you don't really have any intermediate data and you're just rendering directly from source? Can you do this in a comprehensive way on any platform? And in codes like Uinta, you have this question of can you do this from within the compute code? In conclusion, I think there are compelling reasons to investigate Intel as a platform for Viz, both from research and production. I don't think it's a question of GPUs or CPUs. Obviously, you have to use both. But I think it's an interesting area, and I'd like to see more done in this area. And certainly for users of Theta and Aurora, we think OSPRay will be useful in production use cases and also in research. And I think I'll just take it offline there and answer any questions if there's time. Yeah.
What is programming model, parallel programming model to support distributed memory systems in OSPRay?
Yeah, that's a good question. So, obviously for single node, it's ISPC and TVB, as I said in the talk. Right now we have, the OSPRay team has its own sort of distributed parallel renderer, which is available. It has, I'd say, a lot of limitations. That's one of the reasons why we're interested in working with the VL3 team on their software. Certainly, host software like ParaView and Visit can just call OSPRay and use it the same way, uses any other renderer in parallel, but that has its own limitations. It basically means that it's responsible for data distribution, and it largely uses VTK for that, and that's a fairly high overhead solution, but not necessarily a bad one. So in short, there is no specific solution for MPI, but there are lots of different possibilities.
I'm trying to, I don't know anything about Viz, but I'm trying to understand. So the compelling reasons to use this is, it might be maybe more convenient for somebody at university. You could have like a Xeon 5 cluster with a lot of memory, and you can render it yourself.
So I think one really good example would be someone who just wants to be able to do Viz and doesn't want to have to reserve 64 nodes of a cluster just because he happens to have a multi-terabyte or multi-petabyte data set. I think that's really sort of the best use case, where all of a sudden, instead of 128 or 256 nodes, like on most of the cluster, to handle what's really I guess a capability Viz job, all of a sudden you can tackle the same problem, maybe not quite as effectively or in the same way, but you can tackle the same problem on maybe a few large memory nodes, or just a handful of nodes of Theta, which have like 192 gigs of memory. So I think that's where it really starts to get interesting. Not so much frame rate, but
when you
size.
say the GPU is faster, is it kind of same order of magnitude, or is it?
Oh, for small stuff, the GPU is going to be multiple orders of magnitude faster.
Okay.
But for big stuff, once you hit the PCI bus, the KNL or CPU will be multiple orders of magnitude faster. So it's pick your poison. Yeah.
Experiments were made in one box. So what's your opinion when you mix OpenMP and MPI to do visualization?
Yeah, I mean, as I said, that's one of the reasons we want to work with the VL3 team, is to get a better handle of what you do for MPI at scale. I mean, we do use, I guess the single nodes vary a lot, and certainly when I was doing initial research, stuff like PKT tree, having a big beefy CPU workstation, especially before KNL was out, that was really indispensable. But I think also, if you're a Viz user and you just want it to work and you have a large memory source, then it's not a bad solution either. I mean, it does make setup a lot easier. So I'd say the all of the above solution is good, where you have MPI, but you also just can use a large memory node and single node.